अब बेटा आज मुझे आपको ना 2-3 चीज़ें करानी है. 2-3 important things I will be covering up with you before we proceed ahead. Mercator sailing you have told. Mercator sailing I will proceed, but after covering these topics. Now these are some typical questions in great circle sailing and composite sailing. Okay, what are these typical questions? Now in some of the great circle sailing questions, they may give you 3 angles. Last lecture also somebody told that there is a question in which 3 angles are given. So I will tell you today that how these kind of questions can be approached, how they are to be solved, where 3 angles are given. Because cosine formula will not apply, Napier's rule will not apply if there is nothing equal to 90 degrees. So what is to be done there? For that we have to understand the concept of polar triangles. So I will show you that concept. And along with that concept, I will tell you one more complicated, tricky question. It has not come in the exams yet, but if anytime somebody tries to put a bouncer, so you will have an idea how this is to be approached. तो पहले मैं ये आपको बताऊंगा. Then I will show you a typical question in composite sailing. What is that typical question? When the limiting latitude becomes equal to the latitude of one of the ports, then the composite sailing question becomes little tricky. So ये मैं आपको दिखाऊंगा. One by one we will see these 2 topics, and after this then I will take you to other sailings, plain sailing and Mercator sailing, and I'll clarify how those sailings are done. Right, beta? Ready?
Yes.
Ready to go ahead?
Yes.
Okay. So today's topics are little tricky and you need to pay attention. So have a cup of tea, coffee ready with you and pay your attention. These are important and complicated topics. So let's go into them one by one. So beta, first I am taking you to the concept of polar triangles. Let's go. Let's now go into the concept of polar triangle. First of all, we will understand what is the need or use of this polar triangle concept. Now we are aware that the cosine formula can be used in 2 situations, in 2 conditions. One, when all the 3 sides of a spherical triangle are known to us. And second, when any 2 sides of a spherical triangle and the included angle is known to us. Cosine formula can be used only in these 2 scenarios. Now cosine formula cannot be used if we know 3 angles of a spherical triangle. Let me show that in a diagram to you. We have this spherical triangle PAB, Papa Alpha Bravo. And you can see that these green tick marks indicate that we know all the 3 angles of this spherical triangle. If all the 3 angles are known, we cannot solve this triangle or we cannot find the remaining part of this triangle using the cosine formula. That is the limitation of the cosine formula. Also, if we have a scenario in which we know any 2 angles and the included side of a spherical triangle, like in the bottom diagram, you see we know angle A, angle alpha, angle Bravo, and we know side alpha Bravo indicated by the green tick marks. Now in this situation also cosine formula cannot be used. Now in all these scenarios the question can be solved by using the polar triangle concept. So these are the situation where the polar triangle concept comes to our help. Clear up to here, beta? Great, very
Yes,
good.
sir.
Let us now understand what is a polar triangle and what are its properties so that we can use this information to solve these type of questions. Now, every great circle has two poles. The pole of a great circle is equidistant from all the points or all the positions on that great circle. And that pole is also 90 degrees away from all the positions on that particular great circles. We can take the example of the equator on the Earth's surface. Equator is a great circle, and the North Pole is the pole of the equatorial great circles. We are aware that this North Pole is equidistant from any point or any position on the equator, and also this pole is 90 degrees away from any position or any point on the equator. So the geographic North Pole is the pole of the equatorial great circle. Now, when we draw a spherical triangle, we know that each side of a spherical triangle is part of a great circle. Now, if we draw the poles of each of the three sides of a spherical triangle and we join those three poles together with each other by great circle arcs, a new spherical triangle will be formed. This new spherical triangle, which is formed by joining the poles of the great circles of a spherical triangle, is known as the polar triangle of that spherical triangle. Now let me explain this to you using a diagram. We take a spherical triangle. You can see the spherical triangle ABC Alpha Bravo Charlie coming up on the screen now. Now all three sides of this spherical triangle are arcs of great circles. So let's first take the example of side BC, the red color side, Bravo to Charlie. This Bravo to Charlie is part of a big great circle. Now let us assume that this great circle corresponding to side Bravo Charlie has its pole at this particular point. You can see this point A dash, alpha dash coming up in the diagram. This point A dash or alpha dash is the pole of the great circle track Bravo to Charlie. Now, likewise, the second side of this spherical triangle, let's take the example of side alpha to Charlie, the blue color side. This side is also part of a great circle. Let's assume that the pole of this great circle is at this particular point Bravo dash. You can see point Bravo dash coming up in the diagram now. This point Bravo dash is the pole of the great circle track Alpha to Charlie. And now let's take the example of the third side. The third side of the spherical triangle, green color side, is Alpha Bravo. Let's assume that the pole of this great circle track Alpha Bravo is at this particular point represented by C dash, Charlie dash. So Charlie dash is the pole of the great circle track from Alpha to Bravo. Now we have the poles of all the three sides of our spherical triangle. Let's join these poles using great circle arcs. So let's join Alpha to Bravo using a great circle track. You can see the great circle track now, which is joining Alpha dash to Bravo dash. Let's now join Bravo dash to Charlie dash using another great circle. You can see this red color great circle joining Bravo dash to Charlie dash. And let's now join Alpha dash to Charlie dash using another great circle. This blue color great circle is joining Alpha dash to Charlie dash. This bigger triangle which we see in the diagram now, Alpha dash, Bravo dash, Charlie dash, which is made by joining all the three poles using great circle arcs, is known as the polar triangle. The original spherical triangle which we had, that is the smaller triangle Alpha Bravo Charlie triangle, this is called as the primitive triangle of the polar triangle. So the smaller triangle is known as the primitive triangle and the bigger triangle is known as its polar triangle. So the same thing what we discussed is mentioned here. Alpha Bravo Charlie is the primitive spherical triangle. Alpha dash is the pole of side BC, side Bravo Charlie. Bravo dash is the pole of side AC, Alpha Charlie. And Charlie dash is the pole of side AB, Alpha Bravo of the primitive triangle. And A dash, B dash, C dash is the polar triangle of the spherical triangle ABC. Now, once we understand the concept of polar triangle, we can go into its properties, which will help us to solve these kind of questions. Any doubts up to here, beta?
Yes, sir. One doubt, sir.
Go ahead.
This angle at A and the angle at A dash, will they be same, sir?
No, beta, they will not be same. They will be different.
Okay, sir.
Okay, beta. Great. Very good. Now, a very important property of the polar triangle is known as the supplemental theorem. Let's try to understand what this supplemental theorem is. This theorem says that the sides of the polar triangle are the supplements of the corresponding angles of its primitive triangle. Two values are known to be supplements of each other if they add up and total to 180. So let's try to understand this property using this diagram. Now the sides of the polar triangle are alpha dash, Bravo dash, Charlie dash, and alpha dash to Charlie dash. Now if we pick up a side of the polar triangle, let us for our first example pick up the side, red color side, Bravo dash to Charlie dash, and we pick up a corresponding angle of the primitive triangle. Now in the primitive triangle we have three angles, alpha, Bravo and Charlie. The angle corresponding to side Bravo dash Charlie dash is angle alpha. You can also understand it easily by considering angle alpha is opposite to side Bravo dash Charlie dash. The supplemental theorem says that the side of the polar triangle Bravo dash Charlie dash and the supplement and the corresponding angle of the primitive triangle, that is angle alpha, are supplements, means they add up to 180 degrees. That is exactly what is mentioned here. Bravo dash Charlie dash plus angle alpha is equal to 180 degrees. So let us correlate it with the text of the theorem. Side of the polar triangle, the side of the polar triangle taken is Bravo dash Charlie dash, is the supplement of the corresponding angle of the primitive triangle. The corresponding angle or the opposite angle of the primitive triangle is angle alpha. Both of them add up to 180 degrees. So this basically tells us that if we know angle A of the primitive triangle, 180 minus angle A will give us the side Bravo dash Charlie dash of the polar triangle. So you can see this red color angle appearing in the diagram now. This red color angle alpha of the primitive triangle is the corresponding angle of side Bravo dash Charlie dash of the polar triangle. Now likewise, if you pick up the blue color side of the polar triangle, that is alpha dash to Charlie dash, the angle corresponding to it in the primitive triangle is angle Bravo. You can see angle Bravo is opposite to side alpha dash Charlie dash. It is represented in blue color, matching with the side A dash C dash of the polar triangle. So side A dash C dash of the polar triangle plus the corresponding angle of the primitive triangle, which is angle Bravo, add up to total 180 degrees. So if we know angle Bravo of the primitive triangle, 180 minus angle Bravo will give us alpha dash Charlie dash, or the corresponding side of the polar triangle. Now taking it to the third side of the polar triangle now. The third side, green side, which is alpha dash Bravo dash. The corresponding angle to this side in the primitive triangle is angle Charlie, represented by the green color angle. The sum of these two, alpha dash Bravo dash plus angle Charlie of the primitive triangle, is also 180 degrees. Now moving further, the angles of the polar triangle are the supplements of the corresponding sides of its primitive triangle. Now let us have a look at the angles of the polar triangle. We have three angles: angle alpha dash, angle Bravo dash, and angle Charlie dash. The supplemental theorem says that all these three angles are supplements of the corresponding sides of the primitive triangle. Now let's follow this property one by one. Let's pick up angle alpha dash first. We have marked this angle in red color. Angle alpha dash and its corresponding side, mean the side opposite to it in the primitive triangle, is side Bravo to Charlie. Bravo to Charlie is the red color side. So angle alpha dash plus Bravo Charlie side of the primitive triangle will add up to 180. You can see that noted down here. Alpha dash plus side Bravo to Charlie of the primitive triangle is equal to 180. So you can match it with the working now. Angle of the polar triangle, which is angle alpha dash, and the corresponding side of its primitive triangle. Corresponding side of the primitive triangle is Bravo to Charlie. They add up to 180, or both these parts are supplements of each other. We can follow this with the second angle. Let's take example of angle Bravo dash. Angle Bravo dash and the corresponding side of the primitive triangle, which is alpha to Charlie, will also add up to 180 degrees. Let's now understand this with the third angle. Third angle of the polar triangle is angle Charlie dash. Angle Charlie dash plus its corresponding side of the primitive triangle, which is alpha to Bravo, they will add up to 180. This is the supplemental theorem. Now, if we know the sides of the primitive triangle, then 180 minus the side will give us the corresponding angle of the polar triangle. So if any one of the two items is known, the other item can be easily calculated using the supplemental theorem. Any doubts up to here, beta? Very good, beta. Great. Let's now apply this supplemental theorem in scenarios where cosine formula cannot be used. Let's pick up the first scenario, that we know the three angles of the primitive triangle. You can see the known parts of the primitive triangle marked by green tick marks. We know all the three angles of the primitive triangle: angle A, angle B, angle C. All three are known. Now we want to find the remaining parts of the primitive triangle, that is the three sides. Cosine formula cannot be used in this condition. So let's now see how supplemental theorem helps us here. Now we are aware that angle A of the primitive triangle plus side Bravo dash Charlie dash of the polar triangle, these are corresponding parts, they add up to 180 degrees. So if we know angle A of the primitive triangle, 180 minus angle A gives us side Bravo dash Charlie dash of the polar triangle. So we can easily find out side Bravo dash Charlie dash. Likewise, angle B of the primitive triangle plus side alpha dash Charlie dash of the polar triangle add up to 180. So 180 minus angle Bravo gives us side alpha dash Charlie dash of the polar triangle. You can see this green tick mark coming here. And likewise, angle C of the primitive triangle plus side alpha dash Bravo dash of the polar triangle also add up to 180. It's mentioned here. So 180 minus C will give us side A dash B dash of the polar triangle. So you now see we have all the three sides of the polar triangle available to us, and we can now apply the cosine formula to the polar triangle, and by applying the cosine formula we can find all the three angles of the polar triangle. Angle A dash, angle B dash and angle C dash can be easily obtained using the cosine formula. And once we have these three angles, 180 minus these three angles will give us the corresponding parts of the primitive triangle. So all the sides, 180 minus angle A dash will give us side BC, Bravo Charlie. 180 minus B dash will give us side AC, Alpha Charlie. And 180 minus angle C dash of the polar triangle will give us side Alpha Bravo of the primitive triangle. So you see, using this polar triangle concept, we can easily obtain the remaining part of the primitive triangle. Any doubts, beta?
So just one doubt, sir. Not a doubt. Just want to clear on something. As
Go
you said,
ahead.
after finding A dash B dash and B dash C dash and A dash C dash, so we got three sides of the triangle, spherical triangle, and after that we can apply a cosine formula, right, sir, to find out A dash B dash and C dash.
That's right.
Okay, copy that, sir. Thank you.
Right. You apply the cosine formula, get the three angles of the polar triangle. 180 minus those gives you the sides of the primitive triangle. Okay, beta. Great. Very good. So that was the concept of polar triangle. Let's move ahead. Now let's see a second scenario. Let's assume that we have two angles, angle Bravo and angle Charlie, known to us for the primitive triangle, and we have the included side, side Bravo Charlie. Now again you see cosine formula cannot be applied directly to the primitive triangle. Cosine formula is applicable only if we have all the three sides or we have two sides and a included angle. So cosine formula not applied. So what we can do now is use this supplemental theorem to find the parts of the polar triangle. So let's do that. Now we are aware that side Bravo Charlie and angle A dash of the polar triangle are supplements. 180 minus side BC gives us angle A dash of the polar triangle. Likewise, 180 minus angle Charlie gives us the side A dash B dash of the polar triangle, and 180 minus angle Bravo of the primitive triangle gives us side Alpha dash Charlie dash of the polar triangle. Now if you pay your attention to the polar triangle, we have two sides, Alpha dash Bravo dash and Alpha dash Charlie dash. These two sides are now available to us, and we have their included angle also, angle Alpha dash, available to us. So two sides and a included angle available to us, we can apply the cosine formula in the polar triangle and find the remaining parts. First we can find the side Bravo dash Charlie dash of the polar triangle, and later on if we want we can find angle Bravo and angle Charlie of the polar triangle, angle Bravo dash and angle Charlie dash of the polar triangle. Once these three parts are known, 180 minus these three parts will give us the corresponding parts of the primitive triangle. 180 minus Bravo dash Charlie dash side will give us angle A of the primitive triangle. 180 minus angle B dash will give us side AC alpha Charlie of the primitive triangle. 180 minus angle C dash will give us side alpha Bravo of the primitive triangle. So the remaining parts can be easily obtained. Any doubts in this, beta?
This type of questions then become a very lengthy question, no sir, to solve?
Yeah, not very lengthy, beta. You see, it is only 180 minus a particular part. It is done in the beginning and it is done in the end. These two steps are added. Otherwise, it is like a simple application of the cosine formula. So two steps are added. Yes, it will be lengthier than a normal question.
Okay, sir.
Okay, all right, beta. Great. Now, beta, before I proceed ahead, tell me one thing. Now, there is one tricky concept in great circle sailing which has not come in the exams. अभी तक वो आया नहीं है exams में. So I just want to check with you, shall I cover that with you? I don't want to overburden you. So you can tell me, shall I cover that with you if it is comfortable? And if it is overwhelming, then we can leave that also. It has never come in the papers till now.
Yes,
so how would you like to go?
Sir, it's better to just go through over it once.
Very good. So don't take load, okay? Just understand the method. If you see any question, अभी तक नहीं आया है, but if somebody puts a bouncer to you in this kind of format, then you will be able to solve it. Okay? तो मैं आपको बता रहा हूँ, but don't overburden your mind with it. Huh? Take it very lightly, comfortably. Have that with you as a reserve weapon. Okay? Okay, let's go.
सर पोलर ट्रायंगल का भी बहुत रेयरली आता है ना?
Yeah, it comes rarely, beta. In fact, it had not come for last about 10 years or so. But a couple of papers back, they had given the polar triangle question. So that's why it can be repeated anytime now.
Okay, sir.
Sir, you have any
No.
worked example for this type of problems, polar triangle?
A polar triangle?
Yes, sir.
Okay, if you want, I'll share one with you.
Yes, sir. Yes, sir.
I'll share, beta.
Okay, sir.
Just remind me if I lose track, I'll share.
Okay, sir.
Okay, all right. So let's do the typical case. Let's go. Now let me show you another tricky and complicated question involving the solution of a spherical triangle. Till now we have been able to solve the spherical triangle either by using the cosine formula or Napier's rule or by using the polar triangle concept. But there are few more possibilities in which a question can be framed. What is to be done in those cases? Now these questions can look very tricky and complicated, or these are typical type of questions. So let's understand how they can be solved. Let's take the first scenario, that we are given any two sides of a spherical triangle and we are given one excluded angle. Let me show that to you in the diagram. Let's assume that we are given side alpha Bravo AB, the green color side, and we are given the side alpha Charlie, blue color side. You can see green tick marks coming here. These parts are given to us. And we are given angle B, angle Bravo of this triangle, again shown by a green tick mark. Now we cannot use the cosine formula here, and also we cannot use the polar triangle concept here. Both of them are not going to work out. So what is to be done in these scenarios? Now for these type of questions, we need to drop a perpendicular from one vertex to the opposite side. Now when we drop a perpendicular, there are three vertices in the triangle. We have vertex A, vertex B, vertex C, Charlie. Now which vertex should we choose or pick up to drop a perpendicular? So for this, remember that the perpendicular to be considered for our solution should be the one that does not divide any of the sides or angles whose value is given to us. Like say for example, if I pick up vertex Bravo and I drop a perpendicular from vertex Bravo to side Alpha Charlie, AC side. Now this perpendicular is going to divide angle B. Angle B is given to us, so we are not going to use this option. This is going to divide side Alpha Charlie also, which is again given to us, so we will not use that option. Another option possible to us is vertex Charlie. If I drop a perpendicular from Charlie to the opposite side, that is Alpha Bravo, again you see the side Alpha Bravo is given to us. So this perpendicular is going to divide the given side Alpha Bravo. So this is also not to be considered. Now if you come to the third vertex, that is vertex A, if I drop a perpendicular from vertex A to the opposite side, which is BC, Bravo Charlie, now you see angle A is not given to us, its value is unknown, and side BC is also not given to us, its value is unknown. So this is the perpendicular to be considered for our solution. So I will repeat once again. The perpendicular to be considered for solving the spherical triangle should be the one that does not divide any of the sides or angle whose value is given. So it should be joining a vertex and a side whose values are unknown. So let's drop a perpendicular now. So you can see we have a perpendicular dropped from vertex A to side BC. Since it's a perpendicular, angle made at the joining point of this perpendicular to side BC, let's call that as vector. This is basically also the vertex of great circle track Bravo to Charlie. So this angle vector or alpha vector Bravo is a right angle. Now once you drop this perpendicular, you see there are two triangles which are formed now, Alpha Bravo vector and Alpha Charlie vector. Now if you look carefully, triangle Alpha Bravo vector is a special spherical triangle because one of the angles is a right angle, and we know two parts of this triangle. We know side Alpha Bravo and we know angle Bravo. Using these two parts, we can find out the remaining parts. We can find out angle A, that is Bravo Alpha vector angle. We can find side Alpha vector, and we can also find side Bravo vector. So once these three parts are solved, we can now go to another triangle Alpha Charlie vector. Alpha vector has been found out already. Using alpha vector and Alpha Charlie, which is also known, we can find the remaining parts. We can find vector Charlie and we can find angle A. So all the unknown parts in this triangle can be obtained by using this technique. So is that clear, beta?
Sir, जो angle में ये cut कर रहा है vector, is that always the vertex or
that will always be the vertex, beta, because we have dropped a perpendicular. So angle vector will be 90 degrees and it will always be the vertex.
Even if we are going from if initial position is north and final position is south?
Yeah, it will always be the vertex, beta. It will always be the vertex.
So even if the vertex is forming outside the great triangle?
Yes, even if it is outside, you will come to know when you calculate side Bravo vector. Okay, when you will calculate side Bravo vector, you will come to know that the magnitude of Bravo vector is such that it has gone outside the triangle. Okay, you don't have to bother about it. You start it in this particular way only and solve using Napier's. Once you get the values of all these items, it will immediately tell you whether the vertex was inside or outside.
Sir, just one doubt, sir. You said we can't use that polar triangle in this.
Right, beta?
Yes, sir. Just one clarification. Why like that, sir?
Okay, beta. If you use the polar triangle in this, beta, the polar triangle will give you two angles and one side, and that side will not be the included side. So you will have two angles and one side of the polar triangle. Again, cosine formula cannot be used in that situation.
Okay, sir.
Okay. Okay, beta. All right. So this was one case. Now there is one more type of question which can be framed similar to this, but that's case number 2. So let's see that.
So these
case
are the
number.
cases that you're saying that have not come in the exams.
Yes, that's right, beta.
Okay, sir.
Okay. So let's see case number 2 also. Let's now see another similar kind of scenario, and the same technique can be used in that scenario also. Now in this case, we have two angles of a spherical triangle and one excluded side. In the previous example, we had two sides and one excluded angle. Here we have two angles and one excluded side. Let's show them in the diagram. You can see these green tick marks indicate that we know angle Bravo of this triangle and angle Charlie of this triangle, and we are also aware of what is side alpha Bravo, all indicated by green tick marks. Now we cannot use cosine formula here. It does not fulfill the criteria for cosine formula. And also we cannot use the polar triangle concept. Even that will also not be able to solve this. So again, we follow the same technique. We drop a perpendicular from one of the vertex to the opposite side. Now, which vertex shall we pick up? There are 3 vertices. The vertex or the perpendicular to be considered should be the one that does not divide any of the sides or angle whose value is given. So if I pick up angle Bravo as my vertex and I drop a perpendicular, angle Bravo is given to me. So this should not be picked up. If I pick up angle Charlie, again the perpendicular is going to divide angle Charlie. So this also should not be picked up. And if I pick up angle alpha, now angle alpha is unknown, and I drop a perpendicular to side Bravo Charlie is also unknown. So this perpendicular should be considered, where the vertex as well as the side which this perpendicular is joining, both of them the value is unknown. So let's drop a perpendicular. You can see the perpendicular now coming up. Let's mark the perpendicular point as V. This is the vertex of the great circle track Bravo to Charlie. Now exactly in the same way as we solved the last example, you see alpha Bravo Victor, special spherical triangle having a right angle. Beta, mute your mics.
Praveen.
Okay, I'm muted. 2 parts are known, alpha Bravo and angle Bravo. We can find out all the remaining parts. And after this, we can go to triangle alpha Charlie Victor. And using alpha Victor and angle Charlie, we can find all the remaining parts of alpha Charlie Victor triangle also. So using this technique, the same technique, both these complicated and tricky questions, typical cases can be easily solved.
Sir, I want to ask some query regarding in this diagram, sir.
Go ahead, beta.
Sir, you said we should select any angle, sir. Like you select angle 1, sir. So, how we'll know this angle should be selected for dropping the perpendicular? Can you give explanation, or can you repeat this part only, sir? Because here
Okay.
third point is written perpendicular to be considered should be one that doesn't divide any
I'll
of
tell
the
you.
side
I'll
or
tell
angle.
you. I'll
Yes,
tell you.
please.
Okay. Now, beta, when you pick up a angle to drop the perpendicular, angle A, angle B, or angle C, one of the vertex of the triangle you are picking up, which one should we pick up? तो आपने ये ध्यान रखना है, you should pick up a angle which is unknown. Now you see angle B is known to us. We cannot pick this.
Okay, sir. I got now.
Angle C
Whose
known
value
to
is
us.
unknown? Yes, sir.
Yes, we cannot pick angle C also. Angle A is unknown, so we will pick up angle A. Also, the perpendicular is dropping on side Bravo Charlie, and Bravo Charlie is also unknown. So this is the perfect perpendicular drop.
Okay, sir. Thank you very much, sir.
Okay, beta. Great.
सर इसका क्वेश्चन अगर आना होगा तो how will it be, sir? मतलब कुछ any example is there for that?
Okay, I will not give it to you right now. Okay. Later on, if you want, I will give you. For now, concentrate on the ones which are coming in the exams, beta. Later on, if you tell me, I will provide you with a question having this funda also. Not now.
And one more
Okay,
thing, sir. And we are dropping it, so we'll have to put a comment in saying that we are just taking the vertex or something.
No, you
If
just
we
write there, we are dropping a perpendicular from A to side BC. That's it.
That's it. Okay, sir.
That's it. Okay, beta. Great. So, shall I close this out?
Yes, sir.
Very good, beta. Great. So, I'm closing this down now. We are completed with the great circle sailing. Okay. Now, beta, the IT department tells me that some of you may be connected with two devices. So please connect with one. Huh? Okay. Okay. All right. Now, beta, I'm going to take you to a tricky question in composite sailing. Okay. So I will show you what is that complicated question and then how it is to be attempted. So this is what we are going to see. So let's go. Let me set up the presentation. Let us now try to understand a typical problem which can be asked to us in composite sailing questions. Now, if you look at a composite sailing question and you observe that the limiting latitude matches with the latitude of one of the ports, either the initial port or the final port or final position. How to approach these type of questions? Let us try to understand it by making a diagram. You can see the initial position of the ship represented as A. You can also see the final position of the ship now represented by B, Bravo. Let's mark the limiting latitude. In this question, the limiting latitude which they have given us matches with the latitude of port B. So you can see this red color dotted line showing the limiting latitude, and it exactly matches with the latitude of our final position, Bravo. Let us mark the pole. Let us assume that both these positions are in the northern hemisphere, and we can see the North Pole coming up here. Let us now mark the meridian of our initial position A. You see the Papa Alpha meridian of position A coming up. Let us mark the meridian of the destination position B. You can see Papa Bravo as the meridian of the destination port Bravo. Now in these questions, we start on a great circle track which passes from our initial position A, and it has its vertex on the limiting latitude. So you can see this green color track coming up. This should be the first track of our composite sailing. So this is the first part of our composite track, the GC track from Alpha to this particular point here. Now this point on the limiting latitude is where the vertex of this great circle track is, and let us mark this as Victor 1. Now from Victor 1, we start to proceed on the parallel track, and when we are moving on the parallel track, we will reach up to our destination position Bravo. There will be no third leg of our composite track here, because when we are moving on the limiting latitude, position B lies on the same latitude, and moving on the limiting latitude following a parallel track, a Rumline track, we are going to reach to our destination. So we would not require or need to make a third triangle, making a great circle track from limiting latitude to the destination position. That third triangle is not required here. Only two triangles will be made. Let us now mark the meridian of the vertex. We can see Papa Victor 1, the meridian of the vertex coming up. Now we are aware that angle V1, angle Victor 1 is going to be a right angle. At the vertex, the great circle track runs east-west. The meridian of the vertex runs north-south. The angle between them is 90 degrees. Now if you look carefully, we have two triangles in the diagram. We have Papa Alpha Victor 1 and we have Papa Bravo Victor 1. Now out of these two triangles, if you look carefully, the triangle Papa Alpha Victor 1 is a spherical triangle. All three sides of this triangle are parts of great circles. On the other hand, the triangle Papa Bravo Victor 1 is not a spherical triangle, because the side Victor 1 Bravo is not part of a great circle. It is a Rumline track which is part of a small circle. Now once we identify the spherical triangle, the first step in these type of questions is that we solve this spherical triangle. So we will be solving the spherical triangle Papa Alpha Victor 1. Now Papa Alpha Victor 1 is a special spherical triangle. We have a right angle at Victor 1. Napier rule says that if we know any two parts of the special spherical triangle, we can apply the Napier's rule and find everything else. The two known parts of this triangle are, number one, Papa Alpha, which is the colat of our initial position. Initial position is provided to us. And the second known part which we have is Papa Victor 1. This is the colat of the vertex or the colat of the limiting latitude. Limiting latitude is also provided in these questions. So with these two parts known to us, Papa Alpha and Papa Victor 1, we enter into the Napier's rule and we first calculate angle P of this triangle, that is angle Alpha Papa Victor 1. This angle is the d long between alpha and vector 1. If we apply this d long to the longitude of our initial position, we will get the longitude of vector 1 or the longitude of the vertex. Now, once we have the longitude of the vertex known, we can again apply the Napier's rule. And now we can find out alpha vector 1. This gives us the distance along the great circle track alpha vector 1. And we again apply the Napier's rule now to find the initial course using angle A. We find out angle A, that is Papa alpha vector 1. And this angle is used to determine the initial course of the ship using the 1, 2, 3 method, exactly as we did in great circle sailing questions. So once we have the longitude of vertex 1, we also have the longitude of our destination position. We can find out the d long between Bravo and vector 1, and using parallel sailing, we can also obtain the Rumline distance, that is vector 1 to Bravo. And once we obtain this Rumline distance, AV1 alpha vector 1, the GC distance, and vector 1 Bravo, the Rumline distance, combined together give us the total composite distance.
So can you explain again the second triangle, sir? How we get Rumline distance?
Beta, Rumline distance is easy. Once you get the longitude of vertex 1, the longitude of Bravo is already known to you. So you get the d long between them, and you calculate it using the parallel sailing formula. Departure is equal to d long into cos of m lat.
Okay, sir. Okay, sir. Angle P we can subtract and get the V1P angle. Okay, sir.
Yes, that's right.
Okay.
Now the problem arises. This question can be made little tricky and complicated in case we obtain the longitude of vertex 1 and we find out that the longitude of vertex 1 falls outside the triangle PAB. Once you have a look at the longitude of A, the longitude of P, and the longitude of vertex 1, you will immediately come to know. Say, to give you an example, if the longitude of A is 30 degrees east, the longitude of B is 70 degrees east, and the longitude of the vertex 1 from the Napier's rule comes out to be 80 degrees east. Now 80 degrees east has to be east of Bravo, indicating to us that this vector 1 is going to be eastwards of Bravo or outside the triangle PAP. If such a thing happens and the vertex comes outside this triangle, it simply tells us that in these type of questions, composite sailing is not required at all. Since the vertex is being achieved outside the triangle, it simply tells us that even if we follow a great circle track from alpha to Bravo, at no point of time that great circle track will be crossing the limiting latitude. It will always be below the limiting latitude. Since the vertex lies outside the triangle, it tells us that the highest latitude will be attained after crossing our destination position or final position. So in such questions where the vertex comes outside the triangle, we can simply write a remark. As the vertex comes outside, it indicates composite sailing is not required in these questions. And after writing this remark, we can switch over to the GC sailing. We can make a simple GC sailing diagram PAB showing the PAB triangle and solve this using the cosine formula. So if the vertex comes outside, it indicates composite sailing is not applicable, and then we switch over to great circle sailing for getting out the distance between alpha and Bravo.
Sir, in this case, if they ask us to find out the final course.
Okay, if this is a normal question, not the complicated one, then the final course is going to be 090 beta. You don't need to calculate it. It is understood if the vertex is inside and composite sailing is happening, the final course will be 090.
Okay, sir.
Sir, if the
And
V1 comes outside the triangle, but at the initial position के बाहर, मतलब A के दूसरी side, मतलब A angle is more than 90 degree.
Okay. Vertex will never go on the side of A, beta. Vertex will always go on the side where higher latitude is there. So out of A and B, higher latitude is Bravo. Okay.
Right, sir, right.
So same we had this in question 4 and question 6. Both are same type of problems.
Exactly.
In
That's
the
right, beta. That's right. So you will find this remark mentioned there in the solution also. If the vertex lies outside, switch over to GC sailing and find the GC distance. Okay, beta. Great. So is that clear, beta?
Yes, sir. Yes, sir.
Very good, beta. Excellent. So I'm closing this down now. Okay, all right. So beta, the IT department tells me that 2 of the IDs are connected with multiple devices. So please connect with single device. Okay. Please connect with single device. Okay, all right. Now beta, after this, let's take a short break. We will take a 5 minutes break. And after the break, I will take you to other sailings. We will see the plane sailing and the Mercator sailing. Okay, because in some of the questions they tell you to compare the GC distance or composite distance with Rumline distance. So for calculating the Rumline distance, you need to do Mercator sailing. So we will refresh the remaining sailings also. 2 sailings we have covered. In fact, 3 we have covered: Great Circle, Composite, and Parallel. And we will now cover the remaining 2 also: plane sailing and Mercator sailing. So let's be back after 5 minutes.
Okay, sir.
Now there are 3 Rumline sailing methods. These are parallel sailing, plane sailing, and Mercator sailing. There are 2 more sailings in navigation, and those 2 more sailings are Great Circle sailing and Composite sailing. Great Circle sailing and Composite sailing involve complicated concepts of spherical trigonometry. Also, when we are moving on a Great Circle track, a Composite track, the course of the vessel keeps on changing continuously, making the sailing complicated. The Rumline sailings, on the other hand, have the advantage of being the simplest form of sailing. Vessels move on a straight line track. The course of the ship remains the same right from the departure to the destination. Let us now go into these Rumline sailings one by one. Now the first sailing, Rumline sailing, which we have is parallel sailing. Parallel sailing means when the vessel is moving along the parallel of a latitude, or you can say when the vessel is moving parallel to the equator. Now obviously when the vessel is moving on the parallel of a latitude or vessel is moving parallel to the equator, the course of the ship can only be east or west. So that's why in parallel sailing, the course will be east or west, and whether it is east or west on a particular track depends upon the direction of the d long or difference of longitude. When you look at the longitudes of the initial port and the final port, it immediately gives us the direction of the d long, and whatever is the direction of the d long, the same will be the course of the ship, either east 090 or west 270. The distance covered by the ship is given by the formula for departure. Departure is equal to d long into cos of m lat. So we get the d long between the two positions multiplied by the cos of latitude. In a parallel sailing scenario, the mean lat for initial and final ports will be equal to the latitude of both the ports, because both the ports are at the same parallel of latitude. So using this formula, putting the value of d long and the value of latitude here, we get the departure, and this departure is the distance between the initial and final positions. We now move into our second Rumline sailing, that is plain sailing. The plain sailing gets its name from the fact that in plain sailing we use the concept of plane trigonometry. We use the three trigonometric ratios, cos theta, sin theta and tangent theta, for a plane right angle triangle to get our course and distance. All these sailing methods, the Rumline sailing method, parallel sailing, plain sailing, Mercator sailing, as well as great circle sailing and composite sailing, basically allow us to calculate the course as well as the distance between any two positions on the surface of Earth. So in plain sailing, we basically involve our initial and final positions in making a right angle triangle, and when we solve that right angle triangle, we obtain the course and distance. Let us try to understand it using a diagram. Let's assume that the vessel is at this particular position represented by A. This is our initial position, and the vessel intends to reach to its destination, which is at this particular location. Destination is represented by P, that is our final position. Now we involve these positions in making a right angled triangle. Let us see the right angle triangle. You can see a right angle triangle involving our initial and final positions. Now in this right angle triangle, the side A to B, which is the hypotenuse of this right angle triangle, is representing the distance between our initial and final positions. If we measure this distance on a chart, we will be able to get what is the distance between our initial and final positions. Let us name the third vertex of the triangle as C, Charlie. Now, if you look at angle A of this triangle, angle alpha of this triangle, this is the angle between true north. Alpha to Charlie is a vertical line representing true north, and the ship's head. When the ship is moving from A to B, the ship's head will be in the direction of line or vector AB. So this angle is the angle between true north and the ship's head, which basically is the course of the ship. The vertical line or the vertical side of our triangle alpha to Charlie, if this is measured on a Mercator chart, this gives us the d lat or difference of latitude between our initial and final positions. The third side of the triangle, the horizontal side, Charlie to Bravo, if you measure this side on a Mercator chart on the latitude scale, this gives us the departure between our initial and final positions. Now a doubt would arise that the Bravo Charlie line, the horizontal line, can be also measured along the longitude scale. In that case, it will be the d long between our initial and final positions. But always remember that whenever we solve a right-angled triangle, the units in which all the three sides are measured, they have to be the same. Now on a Mercator chart, we have two units or two scales. One is the latitude scale and another is the longitude scale. Now the distance is always measured on the latitude scale. 1 minute of latitude is equal to 1 nautical mile, 1852.3 meters. So this distance is always measured on the latitude scale. Also the side A to C, which gives us the D-lat between the two positions, is also measured on the latitude scale. So the third side also has to be measured on the latitude scale itself. So Bravo to Charlie is not measured on the longitude scale but is measured on the latitude scale itself. When measured on the latitude scale, this gives us the departure between the two positions. The longitude scale and the latitude scale on a Mercator chart are not same. They have different dimensions. So remember that in plane sailing, for all the three sides, we use the latitude scale. Now in this triangle, we have the right angle at point Charlie. And the side opposite to the right angle is the hypotenuse. So distance becomes our hypotenuse. And considering the course angle, the side alpha to Charlie of the triangle becomes the base as it is connected with the angle, which is the course. And the side Bravo to Charlie, which is not connected with the course at all, becomes the perpendicular. So we have a right angle triangle. All the three sides are identified, hypotenuse, base as well as perpendicular. Now let us apply the three trigonometric ratios on this triangle. We first apply the ratio of cos theta. In this case, it will be cos of course. Now cos of course is given by base upon hypotenuse. Base in our case is the D-lat, difference of latitude, and the hypotenuse is the distance. So from this trigonometric ratio, we get our first formula, which is D-lat is equal to distance cos course. So this distance from the denominator is taken to the other side and the relationship converts to D-lat is equal to distance cos course. This is our first formula in plane sailing. Let us apply the second trigonometric ratio now, which is sine of course. Sine of course is given by perpendicular upon hypotenuse. Perpendicular in our case is the departure, hypotenuse is the distance. The sine course ratio gives us our second formula, which is departure is equal to distance sine course. The distance was in the denominator, it is taken to the other side, giving us the second formula for plane sailing. Departure is equal to distance sine course. Let us use the third trigonometric ratio, that is tangent of course. Tangent is equal to perpendicular upon base. The perpendicular in our diagram is the departure and the base is the D-lat, difference of latitude. So we get our third formula, tangent course is equal to departure upon D-lat. Now these are very, very important formulas for plane sailing. Any doubts up to here, beta?
So, what is the reason, sir, for using the right angle triangle?
Why we are using the right angle triangle?
Sir.
Because it
For
makes
plane
the
sailing.
calculation very, very simple and easy, beta. Without using trigonometry, there is no way you can find the courses and distances.
Yes, sir.
Okay, right?
And, sir, and difference between departure and distance.
Okay. Now, I believe this doubt comes from the fact that when we were doing parallel sailing, departure was equal to distance, right?
Yes, sir.
Okay.
Right.
Departure is basically the east-west distance between any two positions. East-west distance. Now, when you are doing parallel sailing, the positions are east-west of each other, beta. They are both on the same parallel of latitude. So departure becomes equal to the distance in that case. But when you are doing plain sailing, then these two positions are not on the same parallel. So departure here will not be equal to the distance. Here the departure is basically telling us that on a Mercator chart, how much A and B are far apart in the easterly-westerly direction. That's it.
Understood, sir. Understood.
Okay, beta. Great. Let's move ahead. Once we are aware of these formula, we can use them to easily calculate courses and distances between any two positions on the surface of Earth. The plain sailing helps us to calculate two basic type of problems. If we have two courses, initial course and if we have two positions, initial position and the final positions given to us, latitudes and longitude is provided. Using this plain sailing, we can easily calculate the course and distance between these two positions. And second type of problem, if we are given a particular position, latitude and longitude, and we are given a particular course and a particular distance, using the initial position, course and distance, we can easily calculate the final position using these formulas very easily. This is a very simple form of sailing. We do not need to refer to any tables. We do not need to use any complicated formulas. Simple trigonometric ratios giving us these three simple formulas, helping us to calculate the course and distance as well as the position arrived using plain sailing. Now, a couple of things to keep in mind when solving plain sailing problems. First thing to note is that we need to make different triangles for different quadrants. Depending upon the direction in which the ship is going, depending upon the quadrant in which the ship is traveling, we need to make a different triangle. In the initial example, we saw the vessel was moving on a northeasterly course. So we used this particular triangle for our plain sailing calculations. This is the triangle for northeasterly quadrant. You can see the course of the ship is in the northeasterly direction. This side gives us the distance, the vertical side gives us the D-lat, the horizontal side gives us the departure. This is the course angle and this is the triangle for the northeast quadrant. Second thing to keep in mind is that whenever we are doing plain sailing calculations, the course which is obtained is always the quadrantal course. It is not the three-figure notation or true notation course. It is the quadrantal course. In case of the northeast triangle, this course is north so many degrees east. If the vessel is moving in the southeasterly quadrant, the initial and final position, latitude and longitude, when we calculate the D-lat and D-long between the initial and final positions, it will immediately tell us what is the direction in which the ship is traveling. So if the ship is traveling in the southeasterly direction, we use this particular triangle. This side is the distance, horizontal side is the departure, vertical side is the D-lat. The course which is used here is the quadrantal course, south so many degrees east. If the ship is moving in the southwesterly direction, we use this particular triangle. Initial position is here, final position is here. Vessel is moving in the southwesterly direction. This is the course angle, the quadrantal course, south so many degrees west. If the vessel is moving in the northwesterly direction, we use this particular triangle. You can see the ship is moving in the northwesterly direction. This angle is the course angle, quadrantal course, north so many degrees west. So whichever quadrant or whichever direction the ship is traveling, we need to use a appropriate triangle for that particular quadrant. Also, the course which is obtained or the course which is used in the formula is always the quadrantal course, not the three-figure notation course. Now there is one limitation which is there in the plain sailing method. And that limitation is that plain sailing is used only for distances less than 600 nautical miles. The reason for that is when we are doing plain sailing, we are solving for courses and distances using plain trigonometry, but the vessel is moving on the curved surface of the earth, a 3D curved surface of the earth. So moving on a curved surface, we are using the formulas which are meant for plane surfaces or plane trigonometry. This is bound to bring in some error in our calculation. Now till the time the distances are small, to be precise less than 600 miles, these errors are small, insignificant, and they can be easily neglected without any appreciable loss in the accuracy. But when the distances become greater, more than 600 nautical miles, the error which comes in our calculation also becomes significant and can no more be ignored. So we use this form of sailing for distances less than 600 nautical miles. What is to be done for distances greater than 600 nautical miles? For that we use our third Rumline sailing, which is known as the Mercator sailing. Any doubts up to here, beta? Great, very good. We now move to our third Rumline sailing, which is the Mercator sailing. We have seen that plain sailing has a limitation of 600 nautical miles. Plain sailing can be used for distances less than 600 miles. If the distance becomes more than 600, it gives appreciable error, significant errors in the answers. Now, Mercator sailing can be used for any distance. Mercator sailing is equally accurate for distances less than 600 as well as greater than 600 miles. Or in other words, you can say that when we do Mercator sailing, the curvature of the earth is accounted for, giving us more accurate courses, distances, and positions. Now, a very simple way to understand Mercator sailing is that when we are making a Mercator sailing triangle or diagram, we convert to the longitude scale on the Mercator chart. By converting to the longitude scale, we are able to obtain the required accuracy. Let us try to understand it using a diagram. We have seen the plain sailing triangle. You can see this plain sailing triangle ABC coming up on the screen. Angle A is the course angle. Side AB was the distance. Side alpha to Charlie is the D-lat. And side Bravo to Charlie was the departure. All the three sides of this triangle were measured on the latitude scale. Now, in a Mercator sailing triangle, we convert to the longitude scale. You can see this blue color triangle shown in the diagram now. This is the Mercator sailing triangle. Let us show the vertices by delta and eco. So alpha, delta, eco is the Mercator sailing triangle. Now, since we are using the longitude scale, when we measure this distance eco to delta on the longitude scale, it gives us the d long between our initial and final positions. When we measure the vertical side, that is alpha to echo, on the longitude scale, this gives us what we call as DMP, difference of meridional parts. If the side was measured on the latitude scale, it gave us the dlat. But if the same side is measured on the longitude scale, it gives us the DMP, difference of meridional parts. Meridional part is basically 1 minute of longitude. So DMP between the initial and final position is basically the number of times 1 minute of longitude can be placed between our initial position and our final position. Now in this Mercator sailing triangle, we have only one additional formula, and that formula is using the tangent ratio. Tangent of course is equal to d long upon dmp. So this formula in plain sailing was tangent course equal to departure upon d lat. It has been converted to tangent course is equal to d long upon dmp. D long can be easily obtained from the chart itself. In fact, we have our initial position and final position given to us. We can obtain the D long between the two positions. The DMP is obtained from the meridional parts table in the Norris nautical tables. As I told you, DMP is the number of times 1 minute of longitude can be placed between the initial latitude and the final latitude, and this is found out using the meridional parts table in the Norris nautical tables. I will show you the meridional parts table in the coming slide. So once we obtain the DMP and the D long, they can be used in the formula to obtain a more accurate course. Now once the course is obtained, to calculate the distance. Now distance cannot be measured using the longitude scale. So for distance we need to go to the latitude scale, because 1 nautical mile is equal to 1 minute of latitude and is equal to 1852.3 meters. So there is no way distance can be measured on the longitude scale. So for calculation of the distance, we go back to our plain sailing formula. D lat is equal to distance cos course. The course has been obtained using the Mercator sailing formula. Same course is used here. The D lat between the two positions is fed into the formula and the distance can be calculated. Now, since we are using the plain sailing formula, how do we obtain a more accurate distance? A more accurate distance is obtained because the course which we have used in this formula is obtained from the Mercator formula, not from the plain sailing formula, and this course is a more accurate course. When you use a more accurate course, the same formula gives you a more accurate distance. Any doubts up to here, beta? Great. Now you may note that in Mercator sailing also we have used the concept of plane right-angled triangle. We have used the tangent ratio. So how are we able to obtain more accurate courses and distances using the Mercator sailing? How is the curvature of the earth accounted for? The curvature of the earth is accounted for by including the DMP, difference of meridional parts. The meridional part basically include the curvature or basically account for the curvature of the earth, giving us a more accurate answer. Mercator sailing, as I told you before, can be used for any distance less than 600 or greater than 600 miles, and it gives us the accurate courses and distances. Let us now see how do we obtain the TMP, difference of meridional parts between any two latitudes. For this we use the Norris nautical tables. Inside the Norris nautical tables, you have a table for meridional parts of the terrestrial sphere. Now in this meridional parts table, you can see the latitudes are mentioned on top on the horizontal axis. You have all the degrees of latitudes, and you see the minutes mentioned on the vertical axis. So you enter with the latitude of the place. For any particular latitude and longitude, you can see the meridional parts from this table. Once you obtain the meridional parts for your initial latitude and the final latitude, these meridional parts are combined together to get the DMP. When combining together, if the initial and final latitude are of the same name, the DMP is obtained meridional parts of higher latitude minus meridional parts of the smaller latitude, bigger MP minus smaller MP. In case the initial and final latitudes are of the opposite names, the positions are in the different hemispheres. In that case, the DMP is given by meridional parts of the higher latitude plus meridional parts of the smaller latitude. Or in other words, the meridional parts of the initial and final positions are added up to get the DMP. This is exactly like how do we calculate the DLAT, difference of latitude between two positions. Same name, we subtract bigger minus smaller. Opposite name, we add both of them to get the DMP. Any doubts now, beta?
So ये vertical वाला is the longitude.
You mean to say in the table, beta?
हाँ sir, in the table.
No, in the table on the horizontal axis, you see the degrees, beta. 10 degree, 11 degree, 12 degree. And on the vertical axis are the minutes.
Minutes, okay, minutes.
Right? So let us say, for example, 10 degree and 10 minutes. The meridional parts will be 609.10.
Okay, sir, okay. Minutes cut out.
Okay, all right. Now, those of you who are not having the Norris table with them, I have shared a selected pages, 25 pages of the Norris table by the name of, I've shared a PDF file with you. It has about 25 pages or so. So these meridional parts are included there in that. You can take a printout of that and you can refer to it when required. Right, beta?
Sir, one out of context doubt. In examination, they will give the Norris table or we have to carry?
Yes, beta. They will provide you with the Norris table. If you want, you can carry your own also, just as a emergency backup. But usually, all the MMDs, they provide you with Norris tables.
Thank you, sir.
Okay, great, beta. So I hope the Mercator sailing, plain sailing is revised now. All revised. सब याद आ गया बेटा?
Yes, sir.
Yes, sir. Yeah. याद भी आ गया और थोड़ा और update हो गया sir.
Very good, beta. Great.
Sir, how often do we use this Mercator sailing in questions?
Okay. See, beta, questions में Mercator sailing पे जो usage आता है, that is basically in these GC and composite questions where they tell you to compare the two distances. Okay. Because when you do GC and composite, the distances are huge, running into thousands of miles. So plain sailing cannot be used there. So that is where we have to use the Mercator sailing. If somebody uses plain sailing there, the question principal error, it will be a principally wrong question. So that is where it is basically used. In other questions, usually Mercator sailing is not required. In plotting questions or in other type of questions, plain sailing does the job. Mercator will
Yes.
not be required there.
So in that vertex questions where we are using composite sailings and all, everywhere we use a plain sailing formulas only, sir.
In composite sailing, you are using parallel sailing, beta.
Parallel sailing. Sorry, parallel sailing.
Yeah. In composite, you are using parallel.
Yes,
In
sir.
plotting questions, or if anywhere you need to find out the course and distance for a short run, you will use plain sailing.
Okay, sir.
Sir, I have one query. I just missed some conversation. I could not hear. When you said DMP, what conditions will we use the DMP, sir? Actually, some
Okay.
phone calls are coming, so I can just miss this point, sir.
No problem. You did not miss much. DMP or Mercator sailing is used in those scenarios where the distances are more than 600 miles.
Okay, sir.
Okay. Because when the distance increases more than 600 miles, plain sailing starts giving us errors in the answers and the errors become appreciable. So that is where we use Mercator sailing.
Okay.
So, sir, to understand more, just to solve, can we Pracnav we can solve the Mercator sailing once, or you will be having some questions now?
No, beta, you are exactly right. What you do is just to practice some basic questions. You have one exercise in Pracnav for plain sailing and one exercise is there for Mercator sailing. So practice some questions from both. Okay. So practice some questions, only those much with which you gain confidence and you are confident that you will do these calculations right. Because these calculations are going to make small parts of our questions. Like हमने देखा Mercator sailing is required in some of the GC composite questions where a comparison is made. Similarly, plain sailing will be required when we go to plotting. Okay, so practice few questions to gain confidence. That's it.
Okay, sir. Thank you.
Okay, all right. Okay. Yeah, question number 4 is now complete, beta. So you complete the assignment which I have given you, and once your assignment is completed, then you can go to MMD past papers also, and you can attempt question number 4 of any paper. And if you get stuck, not getting the answers, not getting the way how to questions getting solved, how the question is to be solved, you can share it on the group. So question number 4 is now completed.
Okay, thank you, sir.
Okay, all right. So beta, next we will be moving on to question number 5 and 6, which involve celestial navigation, sight solving, these concepts. So I will be first covering up the basics of nautical almanac, what all information is there available to us in the almanac, and some basic concepts, correction of altitude, chronometer error, chronometer ambiguity, then calculation of amplitude and azimuth. These basic concepts we will be covering up. I am not picking them up today, so we will keep them for the next class. Okay, so go ahead with your practice of GC and composite beta. Try to complete the GC composite assignment before the next class, because next class शुरू हो जाएगी तो आपको फिर और homework मिलना शुरू हो जाएगा. You will get the practice questions for amplitude, azimuth practice करना पड़ेगा आपको, ABC method, then altitude correction आ जाएगा. So try to complete GC and composite before the next class. That will keep you on track.
Okay, sir.
Okay, all right. So we close out for today, beta, and I will see you in the next class. Before the next class, if you get any doubts in the GC composite assignment, कोई भी doubts अगर आते हैं, so just post them on the group so that I am aware of what doubts are there. If possible, I will send you the solution or a hint how it can be understood over the group itself. If not possible, then I will discuss it in the next class.
Okay, sir.
Okay, beta. So
सर
great.
वो पोलर
हाँ,
तो पोलर ट्रायंगल का सर आप वो जो क्वेश्चन
so I'll send you one question to practice.
ओके सर, थैंक यू.